Hi dear students, welcome back to my channel. Today I am coming with third part of case study questions of chapter 1 electric charges and field. In part 1 and part 2, I already discussed about case study questions based on Coulomb's law, electric field intensity, electric field lines and electric flux. And in this part, I will cover Gauss theorem and its application. Right? But before watching this video, you must go through one short revision of this chapter which is available on my channel and link is given in the description box so that it becomes easy to understand this part. Right? So let us start today's first case study question which is based on Gauss theorem. Now, sixth case study question is based on Gauss theorem. So, to understand this theorem, you must know about electric flux, which already discussed in part 2, right now. It is written here that flux is the property of any vector field. Electric flux is a property of electric field. Mathematically, it is denoted by phi, and this phi, or you can write phi E, electric flux, it is equal to product of given area and normal component of electric field. It means E dot ds. ds is a area vector normal to area. So it is equal to product of this given area and normal component of electric field. Right? Gauss theorem gives a relation between total flux passing through any closed surface. Suppose this is a closed surface S. So Gauss theorem gives idea how much total flux passing through this closed surface. It becomes easy to calculate electric field and flux through any irregular closed surface with the help of Gauss theorem, right? So it gives a relationship between total flux passing through any closed surface S and charge enclosed within the surface. What is Gauss theorem? It states that total flux through any closed surface. If you want to find the total flux through this closed surface S, right now, so how you find? You apply Gauss theorem. It states that total electric flux phi E through any closed surface is equal to 1 by epsilon naught times total charge, this is Q inside, enclosed within the closed surface, right? This is Gauss theorem. It states that total flux through a closed surface is 1 by epsilon naught times net charge enclosed by the surface. Hope you understood this one, right now? Okay. So, electric flux is this one, E dot ds. And according to Gauss theorem, total flux through any closed surface is given by this one. Total charge enclosed within that surface. How much total charge enclosed within this surface divided by epsilon naught. Epsilon naught is permittivity of free space. You know its value. And total flux through any closed surface. Total flux through a small area ds is E dot ds, right now. So through any closed surface, it is represented as integration of this closed surface E dot ds equal to Q by epsilon naught. So with the help of this Gauss theorem, you can easily find total flux and total electric field through any closed surface. It does not depend upon shape and size, right? It only depends upon how much charge enclosed within this closed surface. So here it is written that Gauss theorem is quite useful in calculating electric field in problems where it is possible to choose a closed surface such that electric field E as a normal component which is either 0 or has a fixed value at every point on the surface. This is quite useful in calculating electric field where we consider one closed surface and on that closed surface electric field E is constant or it is 0. It means symmetry considerations in many problems make the application of Gauss theorem much easier. If you find that electric field, you choose that type of closed surface to enclose the charge such that the total electric field on this closed surface is equal to 0 or it is constant. So it becomes easy to apply this theorem, right? The closed surface we choose, that is called Gaussian surface. The closed surface which we choose to enclose the charge is called Gaussian surface. And Gaussian surface may be spherical, cylindrical, cone. It depends upon how it encloses the charge, right? Gauss theorem is based on inverse square dependence on distance contained in Coulomb's law. Any violation of Gauss theorem will reflect a deviation from the inverse square law. So this is written about Gauss theorem in this paragraph. Now you also know about Gauss theorem, where it is applied, what are different conditions to apply Gauss theorem. With the help of Gauss theorem, what you can easily find, what type of body is required, right? Everything you know. So now let us start solving first question number 1 based on Gauss theorem. Okay. Now, question number 1 is, what is the SI unit of electric flux? You know what is electric flux? It is denoted by phi, and phi is equal to E dot ds, product of electric field and area vector. And this area vector is always along the direction of electric field, so that flux is maximum, and if both are perpendicular to each other, in that case flux is minimum. So this is the formula for electric flux. Now you have to find the SI unit of electric flux. So you know what is the SI unit of electric field, then area. You can easily find SI unit of electric flux from these 4 options. So pause the video and try to solve it. A, B, C and D. Which option is correct? Yes. Read fast. Yes. Okay. Hope you find the correct answer. Option number A is correct. Newton per coulomb meter square. How this option is correct? You know electric flux is what? Force per unit charge. It means Newton per coulomb is SI unit of electric field, and ds is area, so SI unit of area is meter square. So Newton per coulomb meter square is correct answer. Hope it's clear to all of you, right? Now next question number 2. Next question is, integration of this E dot ds equal to 0 inside a surface. That means there is, if what is Gauss theorem? According to Gauss law, total flux over a closed surface, it means E dot ds is equal to total charge enclosed within the surface divided by epsilon naught. This is Gauss theorem. Now here it is given that if E dot ds is equal to 0, it means this term is equal to 0. So it means Q, this whole is 0. So which option is correct? Number 1, no charge present inside the surface, uniform electric field inside the surface, discontinuous field lines inside the surface, and D, some charge present inside the surface. If E dot ds is 0, it means Q by epsilon naught is 0, and this implies Q equal to 0. So which option is correct? Yes, write fast. Yes, option number A is correct. No charge present inside the surface, Q equal to 0. Right? In this way, you solve question number 2 also. Now, next question number 3. Question number 3 is, for a given surface, right? The Gauss law is stated as E dot ds equal to 0. From this, we conclude that. What you conclude from this one? Yes. Number 1, E is necessarily 0 on the surface. If E dot ds is equal to 0, what does it mean from these 4? Which statement is correct? E is necessarily 0 on the surface. It means E equal to 0 on the surface. E is perpendicular to the surface at every point. E is perpendicular to the surface at every point. The total flux through the surface is 0. It means phi equal to 0. And the flux is only going out of the surface. Which option is correct? Yes. If E dot ds is 0, it means E dot ds is what? Flux. Flux is what? Surface integral of E dot ds. And if E dot ds is 0, it means charge is also 0. But no option is about charge. Here, option is about total flux. It means if E dot ds is 0, so phi is also 0. Which option is correct? Option number C is correct. Hope is clear to all of you right now. Now, next question number 4. Yes. Here one figure is given. The electric flux for Gaussian surface A encloses the charged particle in free space. Here there are two surfaces. One surface is this one, Gaussian surface B, and the one is this one, Gaussian surface A. The electric flux for Gaussian surface A that encloses the charged particle in free space is. You have to find total electric flux for this surface. It means you have to find first how much charge enclosed within this surface, Gaussian surface A right now. And then you have to calculate total electric flux. What is total electric flux according to Gauss theorem? Yes. What is the formula for total electric flux according to Gauss theorem? Yes. You know, phi is equal to q by epsilon naught. Q is what? Q inside the closed surface. So if you know the total charge inside any closed surface, you can easily find total flux. So what is total charge inside this Gaussian surface A? Q1, Q2 and Q3. Total charge is what? Q1 plus Q2 plus Q3. This is total charge Q inside. Right now, and its value is given here. Q1 is minus 14 nanocoulomb, Q2 is 78.85 nanocoulomb, and Q3 is minus 56 nanocoulomb. Nano means 10 to the power minus 9. Right now, in this way, you find first total charge, how much charge is enclosed, and after that, you have to find flux. If you know what is total charge, then it must be divided by epsilon naught. What is the value of epsilon naught? 8.85. Epsilon naught is what? 8.85 into 10 to the power minus 12. Right now? So, you know epsilon naught, total charge, you can easily find from here. How much charge is there? You just add all these three charges. Minus 14 plus 78.8 plus minus 56. Right? Nanocoulomb. It means when you add these things now, you get total charge 8.85 in nanocoulomb. It means 10 to the power minus 9 coulomb. This is total charge. Now you put these values. The flux equal to 8.85 into 10 to the power minus 9 divided by 8.85 into 10 to the power minus 12. When you solve these things, numerator and denominator, this cut one, 10 to the power minus 9 by 10 to the power minus 12. Yes. Which option is correct? It goes in the numerator, 10 to minus 12 becomes 10 to the power plus 12, and minus 9 plus 12, 10 to the power 3. Right now, so which option is correct? Option number A is correct. 10 to the power 3 Newton meter square per coulomb. Right? In this way, you solve this question. Hope it's clear to all of you. Right? Now move to the next question. That is question number 5. Right? Okay. In this question, it is given that, wait, yes, it is given that charge Q is kept in a sphere of radius 5 cm. There is one sphere of radius 5 cm. In this one, charge Q is placed, and then it is kept in a cube of side 5 cm. Now there is another closed surface, that is cube of side 5 cm. In this also that charge is kept. It means in both this surface Q charge is present. Now the outgoing flux. Now you have to find total flux through this sphere also and through this cube also. So which option is correct? Number 1 will be more in case of a sphere because its radius is more. Then its flux is also more. Think about it. Will be more in case of cube. Third one will be same in both cases, cannot be determined. Think about it. Yes. Pause the video and try to solve it. Yes. Whatever shape it is, whatever is the radius and side of any sphere or cube, according to Gauss Theorem, that closed surface does not depend on any shape and size. Total flux passing through any closed surface just depends upon how much charge enclosed within that surface divided by epsilon naught. If total charge is same, whatever is the shape right now, if total charge is same, in that case flux is also same, right? Total flux through any closed surface does not depend upon shape and size of the closed surface, right? Whatever it is, sphere, cube of any side, any shape, flux remains same. So which option is correct? Option number C is correct. Will be same in both cases, right? Hope it's clear to all of you. Right now? Okay. After this, now 7th and last case study is based on applications of Gauss Theorem. You know there are different applications of Gauss Theorem. Number 1, Gauss Theorem is used to determine electric field due to an infinite long straight wire. Right now, infinite long straight wire. And you know what is the electric field due to an infinite long straight wire? Yes, E equal to lambda by 2 pi epsilon naught r. At a distance r, This is electric field due to an infinite long straight wire. Lambda is what? Linear charge density. In case of continuous distribution of charge, there are three types of charge distribution: linear charge, surface charge and volume charge. So this lambda is linear charge density, charge per unit length, right? This sigma is surface charge density, it is charge per unit area, and this rho is volume charge density, charge per unit volume. These things are also used when you solve different applications of Gauss theorem, right? So here there is another application of Gauss theorem. First one is infinite long straight wire. Second one is electric field due to an infinite plane sheet. Infinite plane sheet of charge, right? And you know what is the value of electric field due to an infinite plane sheet of charge? Yes, E equal to, here we use surface charge sigma by 2 epsilon naught. Suppose there is, this one is suppose a plane sheet of charge, and suppose positive charge is distributed over this plane. Now you have to find electric field due to this plane sheet of charge. So you have to draw first Gaussian surface to enclose that charge. And in case of plane sheet, what type of Gaussian surface is used? Yes, cylindrical Gaussian surface, right? Cylindrical Gaussian surface. And in case of this infinite plane sheet of charge, if charge is distributed over a straight wire, infinite straight wire, here charge is distributed over it. In this case, you draw also cylindrical, long, straight cylindrical Gaussian surface. In both cases, cylindrical surface is drawn, right? So Gaussian surface is of cylindrical type. So here, in case of plane sheet of charge, total electric field is sigma by 2 epsilon naught. If sigma is surface charge density, charge per unit area. If it is negative charge, then it means minus sigma by 2 epsilon naught. So these things you know right now. Now you have to this one. Here it is the parallel sheet of charge. It means there are two sheets which are parallel, kept parallel to each other. You know electric field due to plane sheet of charge. Right now, I already told you this electric field due to an infinite plane sheet of charge is what? Sigma by 2 epsilon naught. Right? Now you have to use this application to find parallel sheet of charge. Now it is written here that there are two plane sheets right now. On one plane sheet, here positive charge is distributed, and another plane sheet, negative charge is distributed. You know, electric field due to this positive plane sheet is what? Sigma by 2 epsilon naught. This negative sheet is what? E equal to minus sigma by 2 epsilon naught. And due to positive charge, E equal to plus sigma by 2 epsilon naught. You know, right? Now here there are two parallel sheets. Now you have to find electric field at different points. So let us read these lines. What is written here? Surface charge density is defined as charge per unit area of surface charge distribution. Here surface charge density is used. This is total charge per unit area. I already told you. Surface charge density is charge per unit area. Two large metal plates are parallel close to each other. These are two A and B are two metal plates which are kept parallel to each other, very close to each other. On their inner faces, the plates have surface charge density on opposite side. This plate A has positive surface charge density and this plate B has negative minus sigma surface charge density. And its value is given 17 into 10 to the power minus 22 coulomb per meter square. This is the value of surface charge density. On this plate, it is plus 17 into 10 minus 22, and on second plate, minus 17 into 10 to the power minus 22. Now, electric field of intensity of electric field at a point is given this one, sigma by epsilon naught. At any point, electric field is given by sigma by epsilon naught between the two plates. Also the plates, I don't know. At any point, it is given here, where epsilon naught is permittivity of free space. So, if you know these things, now you have to calculate total electric field outside, left side of this plate, right side of this plate, in between the two plates, right side of this second plate. At different positions, you have to find electric field. It is easy to solve because you know what is the electric field due to an infinite plate sheet, either positive or negative, you know. So you can easily find electric field at any points. So let us try to solve different questions based on this one. Okay. Question number 1. Question number 1 is, yes, E in the outer region of first plate. Okay. How plates are drawn? There are two plates. One is positive plate, right? Here positive charge are distributed, and here is negative plate. Negative charge are distributed. Both these plates are kept close to each other. You have to find outer region of first plate. This one is first plate and this one is second plate. Outer region of first plate means where? Yes. Outer region of first plate means, suppose this is region 1, this is region 2 in between the plates, and this is region 3. You have to find electric field in the outer region of first plate. This first region you have to find electric field. Now you know here electric field is due to both plates. In this region, the electric field due to first plate, direction of electric field is this direction, EA, right now. And also due to this negative plate, electric field is towards this one, it means this side, EB. So in the region 1, both fields are in opposite direction. So what is the net electric field in region 1? Magnitude of both the fields are same. Due to positive charge, what is electric field? E equal to sigma by 2 epsilon naught, right? And due to this negative plate, electric field is minus sigma by 2 epsilon naught. Now you know it does not depend on distance or anything, only charge density is same. One has positive charge density and the one has negative surface charge density. So in region 1, both fields are in opposite direction. So net field is how much? Yes, guess the answer? Yes, very good. Option D is correct. Electric field outside this first plate is 0. Total electric field is what? EA plus EB, and both are same but both are in opposite direction. EA is what? Sigma by 2 epsilon naught. EB is what? Minus sigma by 2 epsilon naught, and total electric field is 0. In this way you solve this question. Hope it's clear to all of you right now. Now next question number 2. Yes, in this question it is given that electric field in the outer region of second plate, right? How you solve this one? This is first plate, positive charge. This one is second plate, negative charge. You have to find electric field in this region, third region. This one is second and this one is first. So here at this point, electric field due to this positive charge is away from the positive charge. This is the field direction due to plate A, and this is plate B. And here electric field due to this second plate B is in this direction towards the negative charge, negative plate EB. Again at this point also both fields are in opposite direction right now. So total field is what? EA plus EB. EA is what? Sigma by 2 epsilon naught, and EB is what? Minus sigma by 2 epsilon. Total electric field is again how much? Yes, it's 0. Option number D is correct. So it's very easy to calculate if you know how you find the direction of electric field due to positive charge, due to negative charge. You must remember these points. Electric field due to positive charge is always away from the positive charge. Electric field is always towards the negative charge. Right now? Now next question number 3. Here it is given that, yes, electric field between the plates. Now you have to find. You have to already find electric field outside both the plates. Now you have to find electric field between the two plates. One plate is positive, right? And the plate is negative. This is positive plate A. This one is negative plate B, right? And you have to find electric field at this point, region number 2. Now you know electric field due to this positive plate is towards away from the positive plate EA in this direction, and electric field due to this B plate is towards the negative direction. Yes, electric field is also towards the negative plate. Here in this region in between the two plates, both electric fields are in same direction. So how you find total electric field? EA plus EB. EA is what? Yes, sigma by 2 epsilon naught. And EB is also sigma by 2 epsilon naught. But here both are in the same direction, right? So just add these two electric field, you get 2 sigma by 2 epsilon, 2 cancel, you get sigma by epsilon naught. This is total electric field in between the two plates. Now it's given that what is the value of this sigma? Yes, okay. Move to the paragraph. What is the value of sigma given here? Yes, it's given that the value of this surface charge density is 17 into 10 to the power minus 22. Not 17, it's 1.7, right? Not 17. 1.7 into 10 to the power minus 22. Now, how you find electric field in between the two plates? It is formula becomes electric field between the two plates is E equal to sigma by epsilon naught. So you put the value of sigma here, 1.7 into 10 to the power minus 22 divided by epsilon naught. What is the value of epsilon naught? Yes. What is the value of epsilon naught? 8.85 into 10 to the power minus 12. Right? So when you solve these two, you get how much? Solve it. Pause the video and try to solve it. A, B and C and D. Which option is correct? Yes. After solving, you get 1.92 into 10 to the power minus 10 Newton per coulomb. Which option is correct? Yes. Option number, which one? C is correct. Option number C. 1.9 into 10 to the power minus 10 Newton coulomb. So in this way you solve this question also. Now next question number 4. Now question number 4 is what? It is given that the ratio of electric field from right side of B at a distance 2 cm and 4 cm. This is plate A, positive plate. This one is plate B, negative plate, right now. And you have to find ratio of electric field on the right side of B is this one. One at a distance 2 cm from this plate and one at a distance 4 cm from this plate. Right? So, what is, suppose this is E1 and this one at a distance for the E2. Now, you have to find ratio of this E1 by E2. How much? Try to solve it. Yes, it's very simple. It depends upon your concept, how your concept is clear right now. You know, electric field due to plate is what? Sigma by 2 epsilon naught. It depends on the distance from where you are solving the electric field. No. It only depends upon surface charge density. It has minus sigma, it has plus sigma, and this is given whatever is the distance, and epsilon is also constant. So electric field at this point 2 cm from this one is also sigma by 2 epsilon naught, and electric field at this point 4 cm from this plate is also sigma by 2 epsilon naught. It means both electric field are same. It means ratio is also 1 by 1, 1:1. Which option is correct? Yes. Option number C is correct, right? It does not depend on the distance of observation, right now. It only depends upon this surface charge density, which is constant at both the places for a particular plate, and epsilon naught, right? In this way you solve this question also. It's very easy. Now come to last question. Now last question. In order to estimate the electric field due to a thin infinite metal plate, the Gaussian surface considered as, I already told you now, when you want to find electric field due to this thin plane sheet, infinite plane sheet, you have to draw what type of Gaussian surface to enclose these charges? A spherical, cylindrical, straight line, or none of these? Yes. What type of Gaussian surface you have to draw? Yes. Cylindrical surface like this one to find electric field due to this plane sheet at any distance, or you have to use this cylindrical Gaussian surface to find electric field in case of infinite metal plate. So in this way you solve questions one by one. Hope it's clear to all of you. Now, so with this I am going to end the class. So hope these videos are helpful to you. There are 3 parts of case study questions of chapter 1, part 1, part 2, and this is part 3. After this I will start which type of MCQ? Assertion reasoning. Then after that multiple choice question. So keep watching and wait for the next video. Thank you.